This is video 39 in the lecture on the design of reinforced concrete beams. This lecture is part 3 of an overall design of a beam and covers the checks in SLS like stresses, crack width and sag. We have seen in video 37 the durability, loads, strength, depth and the recalculation, the reiteration. Then in video 38 we looked at the shear force and the minimum reinforcement, and now in video 39 we will look at the stress, crack and deflection in SLS and give a summary. First, have a look at the stresses in SLSK. In SLS it's only checking. There is no design that we will do in SLS. So this is the section as it is now. The bending moment in SLSK was 291 kilonewton meter. The reinforcement was tension reinforcement was 4 diameters 25, and the point of gravity of the tension reinforcement is the concrete cover plus the stirrup diameter plus the point of gravity of the reinforcement, which gives you 60.5 millimeters. The compression reinforcement is 339 square millimeters and the point of gravity is 54 millimeters. The effective depth is then the total depth minus D1, it's 599.5. The total reinforcement is 2302. In SLSK, it's a short-term loading, so the creep coefficient is 0. The modulus of elasticity of the concrete is equal to the mean modulus of elasticity, and it's 32,837 megapascal. This means that alpha, which is ES divided by ECM or EC, ES divided by EC is 6.09, which is the expected value. The depth of the neutral axis is the point of gravity of the equivalent cross-section, and X is then 168 millimeters. This should be more than the concrete cover plus the stirrup, otherwise it will the concrete will spoil, it will chip off. So this is okay. The compressive depth, let's put it this way, or the depth of the neutral axis is okay because 168 is bigger than 48. Then to calculate the stress in the top fiber of the compressive stress in the concrete in the top fiber, we can easily calculate that by using the equivalent cracked cross-section. And we arrive at 17.4 megapascal. We must comply with 0.6 FCK, which is 18. So you see that this is very close. Supposedly that we used concrete C16 instead of 630, we should already now be in a big problem. We should choose. We were not able to do it because we will not comply for the compressive stresses in SLSK. Notwithstanding this, a lot of engineers do not check for normal beams like this one, a very normal simple beam. They do not check the compressive stress in SLSK, but we see that this is absolutely necessary. Sometimes it is important to choose the right concrete grade. The steel stress, when we calculate the steel stress, we'll see that we have 272 megapascal, which is far below the 400, and the steel stress in the compression force is also far below the maximum of 400. SLS quasi-permanent is a long-term loading, and the creep coefficient is here not specified. This means that we have to make our own calculation in chapter 3 of Eurocode 2. Then we can use the graphs, and then you will see that instead of calculating it directly, you can also use graphs, that the creep coefficient is 2.15. The bending moment in SLSQ is 254. The effect of the permanent load is is 31. Of the mobile load is 2.1. It means that our K factor, the proportion to the effect of the permanent load divided by the effect of the total load, is 0.937, and the modulus of elasticity of concrete is ECM divided by 1 plus K times phi, which gives you 10,893 megapascal. Or alpha is 18.36, which is around 15, which is okay. Then for the crack width, we calculate the depth of the neutral axis of the cracked section. It's 253 millimeters, which is bigger than the 40 plus 8, so that's okay. And then again, the concrete stress, or the stress in the concrete, but this time in SLSQ, it's 9.9, and it must be lower than 0.45 FCK, which is 13.5. So that is okay. The steel stress in SLSQ in the tension side is 250 megapascal, which is okay, and in the compression side it's 143 megapascal, which is smaller than 0.8 FAK. Then we look if the beam is cracked, so we need the cracking bending moment. Therefore, we calculate the depth of the neutral axis again, but this time for the uncracked section, which is 359 millimeters. We calculate the moment of inertia for the non-cracked section, which is 1.1 times 10 to the power 10. The V, which is H minus XE, is 301. And the W is then 3.73, 10 to the power 7, or our cracking bending moment equals 108 kilonewton meter, which is lower than the MED in SLSQ, which is 254. So it means that the section is cracked. Strain difference. For that, we need to calculate AC effective, which is the width times H, and H is the minimum of 3 values, the minimum of H minus X divided by 3, or 2.5 H minus D, or H over 2. And the minimum is 135.67. And AC effective is 47,485. Then the density of the tension reinforcement is then equal to 0.0413, and the delta epsilon is then equal to 0.998 10 to the power minus 3. But it should be bigger than 0.75, which is the case. So that's okay. So it's 0.998. Then the maximum crack spacing, SR max, is then 3.4 times the concrete cover, plus 0.8 times 0.5, 0.425, the diameter that we use, and then the rho effective. And we have a maximum crack spacing of 239 millimeters. The crack width is then the SR max times the delta epsilon, and gives you 0.2024 millimeters, which is okay because we are here in environmental class EI, which means that we must comply with 0.4 millimeter, which is the case. Now we look at the deflection in SLSQ. The bending moment was 254. creep coefficient 2.15, the cracking bending moment was 108, the load was 33.425 kilonewton per meter. That means that the deflection factor or the interpolation factor is equal to 0.91. 0.5 because we are looking at the long-term deflection. Non-cracked section, we have already calculated the depth of the neutral axis of the non-cracked section, also the moment of inertia. Then we can easily directly calculate the sag of the beam for the non-cracked section, which is 13 millimeters. For the cracked section, we've seen that it was 253 millimeters and the E was 0.65 times 10 to the power 10. Again, you will see here the difference between a non-cracked section and a cracked section. So the difference in stiffness is not neglectable. The sag for the cracked section is 23 millimeters. And the total deflection is then a linear combination between the two with zeta as coefficient. We have 22 millimeters. This also means that if you take only the cracked concrete into consideration, it's 23 millimeters. But if we take everything into consideration, it's 22. So it's close to the 23. That means that almost the whole beam over the whole length is cracked. And the deflection is dominated by the cracked section. And the 22, it's smaller than 26, which is the span divided by 250. Or 300, sorry. Sometimes we take 250, but it is in fact 300. We can now have a summary of the results. The dimensions of the beam is 660 by 350, concrete grade C3037, steel B500, and the concrete cover is 40 millimeters. The reinforcement 4 times diameter 25 as tension reinforcement and 3 diameters 12 as compression reinforcement. Stirrups diameter 8 every 320 millimeters, and the flank reinforcement is 2 diameters 12. In SLSK we have the compressive stress as 17.4 and the steel stress as 272 and 72. In SLSQ we have 9.9 megapascal as compressive force in the concrete and steel stress 249 and 143. The crack width is 0.24 millimeters and the sag is 22 millimeters. You can now perform an overall design of a reinforced beam and see you in next lecture.